Hi, this is our first of a series of video lectures. Today, I'll talk a little bit about statistics in high dimension. And in particular, we'll talk about principal components analysis as an introductory or an initial method to do dimension reduction. All right. So this word or a concept of big data is very popular, and no doubt you heard it many times before. I wanted to just spend a second talking about what big data can mean in different contexts. So throughout the lecture today, we'll let X here be an n by k matrix, n observations with k columns. So n observations, k features. So this matrix can be big in some different ways. So first, an obvious way for it to be large is for n to be large. That is to say, you have many, many observations. So many of you who will go on to work in the private sector or analyze consumer data will see data sets with lots and lots of rows. So maybe, online purchases, census data, and so on. One thing that happens when n becomes large is some complicated statistical algorithms slow down. And some can slow down so much that they can't be run on a single computer. And so the idea of high performance computing and distributed computing comes in handy here. So we're not covering that in this class. That's something that you would study later on in a more advanced computing class. Right, so you might use these high performance computing methods, or another strategy, if you do want to do analysis on your own machine, you could sample random subsets of the data, analyze them, and then bring them together later on. So we've discussed the bootstrap as a resampling method, and this random subset method is somewhat similar to it. But the idea is pretty simple. Say you have 1 million rows, 2 million rows, what have you. Sample a much smaller number of rows, perform some algorithm, perhaps store some parameters, and then continue on, sample another subset, and do the same thing, and then aggregate that later on. Okay, so then aside from n being large, k can be large. So when k is large, this means that there are many variables, features, or dimensions, just depending on what we want to call them. So when k gets large, this is somewhat of a different problem. So some statistical algorithms and estimation routines no longer work. For example, when k gets larger than n, we have issues with OLS. We won't cover that in this class, but that's a problem you may study later on, and you may learn about penalized methods such as ridge regression or the lasso. But importantly, when k gets really large, it can be hard to explore these data sets visually. We have ways to explore data in 2, 3, even 4 dimensions, by doing things like coloring points differently or increasing the character expansion factor of points. But all the same, if you have a truly large number of observations, it is quite difficult. So let's dive in and talk about some possible solutions for large K. So it might be the case in some of these data sets with a large number of features that many of the columns are correlated. If they're correlated, well, then we might think that they contain redundant information. Okay, so if you have, say, 100 columns of data and they're highly correlated, well, perhaps there's a way to decorrelate the columns and create a smaller set of features that would explain the variation in the data pretty well. So there are several methods one can do to do just this. And in the course, we'll cover a few of these, but I'll just mention some of the popular methods. Principal components analysis, which we'll cover in this lecture. Multiple correspondence analysis, we'll cover that later on. That's a technique when you have a high number of categorical features. Factor analysis, we won't cover that in this class. Multidimensional scaling, we'll cover that in a later lecture. Canonical correlation analysis, and then the so-called isomap, which we'll cover later on. So this is just a small list of the number of techniques that are out there. As data sets grow larger and larger, and we begin to collect data on very complex things, for example, DNA. It's pretty common to run into high dimensional data sets, and therefore it's useful to have many different ways to reduce the dimension. Okay, so let's look at an example. We have data on mice protein expression. So this data is available 2 different places. There's a link to Kaggle here. And for those of you who are unfamiliar, Kaggle is a place where people compete in online competitions. There are many different tasks that one can do, prediction, clustering, and so on. But besides being able to compete in competitions, it's also an excellent place to find data sets. And then the second location is this link from UCI, so University of California, Irvine, and they also have a number of wonderful data sets. Okay, so this data has measurements of 77 proteins in mice brains. There are 2 types of mice here. The control, normal brains, and then the other group have an abnormality. So there are 77 quantitative variables in the data. It's quite a lot. So the measurements were also repeated 15 times for each mouse. There's a primary key providing the mouse ID, and then there's some other categorical features in here. So we won't use the categorical features in the ensuing analysis. However, if you'd like to play with this data, it's up on Canvas, and you can do so. So the high dimension, the 77 variables, clearly make this very difficult to visualize. So let's see about ways to reduce the dimension. All right, so first, suppose we didn't want to visualize all 77 quantitative dimensions. So here's one way to do it. This is a heat map. And so what I've done here is I have the first 30 observations in the data. That's the rows. And then see the columns are the different proteins that have been measured. And then the color here indicates the value. So we have these lighter colors indicate higher concentrations of the proteins. So looking at this, we can say something, right? We can say that this particular protein seems to be pretty prominent. So does this one, and a lot of these values look almost the same. It's not clear how much one can say about a plot like this. It's kind of hard to tell how the columns are related. I mean, it looks like some of these are perfectly correlated. Who knows? So although it's a pretty tiled visualization, it's hard to get much out of it, and moreover, it's quite hard to visualize outliers if we were interested in identifying those. All right, so here's some code I used to create the heat map. I used the package Pretty Heat Map. So you can find the data in Canvas. It's called Data Cortex Nuclear. And what I've done here is I've used the Viridis Lite package to make a color palette, and then I use the pretty heat map function to create that graphic you just saw. So this is this can be a nice function to use. All right, so let's take a look at the correlation between the 77 quantitative variables. So this, I've used core plot here, which again is a nice package for visualizing information. And what do we see here? Well, we have a lot of blue squares, and the dark blue squares indicate that the columns of data are correlated. All right, so we have a lot of dimensions, but it appears that many of these dimensions have a high positive correlation. So when one protein is observed, then another is also likely to be observed. So because we see that they're correlated, there's probably some redundant variation here. And so for this reason, this data set is a good candidate for dimension reduction. So here's how I did this. So I've loaded this mice data. I took columns 2 through 78. Those are the 77 quantitative columns of data. I dropped all the observations with missing data, and then I put it into core plot. Okay. So one solution for this is principal components analysis. So again, X will be our matrix. It's n by k. And we'd like to find a lower dimensional representation of our data. We'll call that Z. And we'd like that to be n by L, where L is less than k. So in the mice example, k is 77. What if we can find an L that's 10, right? That might be much easier to work with, much easier to visualize. And we might also think that if many of the columns are highly correlated with one another, that may increase the variance of whatever analysis we're doing, or at any rate, complicate our analysis. All right. So we'd also like Z to be uncorrelated, meaning that the L meaning that these L dimensions are contain non-redundant information. All right. So here's a description of the algorithm for principal components analysis. So find the mean for every dimension in X, compute the empirical covariance matrix of X, compute the eigenvectors and the eigenvalues of this covariance matrix, and then we'll sort the eigenvectors according to their eigenvalues. So you find you'll find the largest eigenvalue, for example, make that, and then make the first eigenvector the eigenvector associated with that largest eigenvalue, and so on like that. And then we'll choose the largest L eigenvalues and form a K by L eigenvector matrix, and this we'll call W. And then finally, we can compute this lower dimensional matrix Z, and that's going to be X times W. And so you see that X is n by K, W is K by L, and so Z will be n by L. Okay. So just briefly discuss a more mathematical description of this procedure. So one way to think about this is to think about reconstructing the original data. And so we'll let xi hat here be an approximation of data point xi. And so now by xi, I mean one of the rows in our data. And so it's k dimensional, because where, for example, k is equal to 77. So we define the average reconstruction error to be the average squared distance between the original data point and our reconstructed data point. Okay. So in principal components, what we're doing is choosing an orthogonal set of L linear basis vectors. These are our WJs, and a lower dimensional representation. These are our ZIs. to minimize the average reconstruction error, where we're defining our approximation to xi to be, so xi hat here is w times zi. Okay. So as we said before, the dimension of w would be k by l. And if we solve this optimization problem, which we won't do in this class, you'll just take the answers as given. We see that in the optimal solution, W, this transformation matrix, contains the L eigenvectors with the largest eigenvalues of the empirical covariance matrix. So the optimal lower dimensional encoding of our data is given by this formula down here. And then again, the reconstructed data is x hat is equal to z hat, the transpose of w hat. Okay, so that's a mathematical description that may or may not be helpful to you. Those of you who have studied optimization might find this pretty interesting. And you can find proofs of this in several textbooks. I'll list a few of those on Canvas for those of you who are interested. Okay, so let's actually see this at work. So I want to plot the observations from the mouse data, and here in this plot I have the first two principal components. So this is my z hat 1 and z hat 2. So z hat 1 is the component associated with the largest eigenvalue, and z hat 2 is the component associated with the second largest eigenvalue. So these two components capture 47.3% of the variation in the data. Okay, so think about this. We had 77 columns of data, and we have 77 principal components, but the first two principal components capture almost or close to a majority of the variation in the data. So that's pretty good, right? This can be useful in a number of ways. So we can look at this picture and see some outlying points, for example. We can also do analysis on this lower dimensional representation of our data. Okay, so here's how I did this. So I first scaled the data. I'm going to talk about standardization in a few slides, about why you might or might not do that before doing principal components analysis. So we'll just hold off on that for a second here. At any rate, I've scaled the data, and then I compute the eigenvalues and eigenvectors. And so there's a function in R called eigen that'll do that for you. And then I get the principal components. So here I am multiplying my data, my scaled data here, times my eigenvectors. So it's a W times X. That's what we're seeing right there. And now I'm plotting the points in 2 dimensions here. And so you see I'm taking the first 2 columns of Z, and I'm labeling the X and Y axes with Z1 hat and Z2 hat. And note, I've used this function expression. And expression will allow you to make to do some math typing in your plots in R. So you can play around with that a little bit if you like. And so what have I done here? Well, I've done a subscript, and then I put a hat on Z. Okay, then I'm adding points, and I've used the rainbow function just to pick some pretty colors. So the colors here don't actually indicate any kind of cluster membership or anything. They're just meant to make the picture a little more visually interesting. And then I've added horizontal and vertical lines to show us the center, the data here. Okay. So we can show that the eigenvalues are actually the variance explained by each principal component. And so this bar plot you see, I have the variance explained by the first 10 components. And so you see the first one is quite large, and there's the second. And those two we saw are about 47.3% of all the variation. And then you can see that the variation trails off pretty quickly. So that might suggest, for example, that with these 10, we can actually explain the data pretty well. And that's what one would hope by doing analysis like this. So as we've said, we would like our this new representation of our data to be uncorrelated. And so I've computed the correlation matrix using core-plot again of Z here. And so this shows the first 30 principal components, and you see that they're not correlated. Okay, so that's good. That's what's supposed to happen. All right, and so here's how I created these. These plots. So I used Viridis to get 10 colors. I extracted the eigenvalues from the object myEigen2. And that's what you see in the bar plot call there. Let's see the names.arg. It gives the names for each of the individual bars you see there. And then down here, I compute the percentage of variance explained by each component. So for those of you who haven't seen it yet, CumSum is a nice cumulative sum, and that's a handy function. And so taking that over the sum of all the eigenvalues will give us the percentage explained by each. Okay. All right. So I mentioned that we have a choice to standardize or not standardize. And I wanted to just take a second to talk about this. So in general, standardizing involves subtracting the mean of each column and then dividing by its standard deviation. And so that's what we've done here. So X prime here is column K just subtracting the mean of column K and dividing by the standard deviation of column K. So what this does is we now know that our data will be centered at 0. So the new data has a mean of 0 and a standard deviation of 1. So why would we want to do this? Well, if the columns of our data are measured on very different scales, then one column that has, for example, very large numbers can dominate the others, leading to one or two principal components soaking up most of the variation. So in that case, we might not think it's the actually interesting variation, but it's rather just the size of the units that's driving the results. So an example here is, say you have the height and the weight of bears, right? And so the weight, so the height you might have measured in, let's suppose you have that measured in meters, right? And then let's suppose we have weight in pounds. Well, we might have a pretty large variation in pounds, and so then the variance there will look pretty big. But then, with meters, the variation in the meters dimension might be pretty small. So this would be an excellent candidate to standardize ahead of time. However, if all the variables are measured in the same units, then standardization might not be so necessary. And in these cases, you might get somewhat similar results between the two methods. So I also want to say that we've learned to look for outliers in the data, and then we know if we're using means and variances that they're not robust to the presence of outliers. And so there are ways to do robust standardization. And you could subtract the median, for example, and then divide by the IQR. Okay, so whether or not you standardize will really depend on the particular application. And that's something that as a data scientist, you need to pay attention to and know your units. And in most cases, the results you'll get can be quite different. Okay. So the next thing I want to mention is the biplot. So the biplot is a way to project our variables into this lower dimensional space. And it allows us to see how our original features relate to one another, and then how they relate to the principal components. All right, so I've decided to do a different example here. We have some data on rental homes in Brazil. This data set has 11 different variables that are measured on really different scales. So some of them are prices. So that's monetary units. We have other things like the number of square feet. We have other features such as whether or not animals are allowed. The floor. So if it's in a building, the floor it's on, the unit's on. So it's pretty clear that we would want to standardize this data. Okay, and we know we've done just that. And in a second, we'll look at the code. All right, so let's take a look at this biplot. So we see some vectors here in red, and these show the relationship between the original variables and the principal components. So let me just walk you through a quick interpretation of this. So we have a variable here, furniture, and that indicates whether or not a home is furnished. We have floor, that's the floor that the unit's on, so 1, 2, 3, 4, and so on. And then we have animal, and that's whether or not animals are allowed. And so we see that all of these features, they're close to principal component 2, right? And that's the vertical black line. And so that means they contribute to that second principal component. We see that bathroom and the number of parking spaces, so bathroom is the number of bathrooms, and parking spaces is the number of parking spaces. They influence or determine principal component 1. The other thing we can get out of this is the angles between these vectors, and they'll indicate how the features are correlated with one another. All right, and so we see that that rooms and area here, somewhat difficult to make out in this plot, but rooms and area are highly correlated with one another, and that makes a lot of sense. If you have a lot of rooms, then the square footage of your place is growing, right? And then we see that, for example, being furnished and allowing animals are negatively correlated. So these vectors point in different directions. And again, that probably makes some sense. If the landlord furnishes the apartment, they likely don't want cats and dogs running all over the place. Anyhow, so we can see how we can quickly learn something about the data set by looking at this this lower dimensional space. So finally, the blue points are the original data points in the first two principal components. All right, so here's some code to do this. So I'm loading in my housing data. I'm then doing some cleaning of the data. And so in this data set, the column animal had accept or not accept, with accept taking a very interesting spelling. So I've recoded it to be binary. The same thing for furniture. And then the floor data, there were a few that had no value, indicating that it's not a multi-level building. And so what I did is I said that if it's a single-story building, then I'll just say the floor is 1. And so that's what I'm doing with those if-else commands. Then I've converted, so everything here is being stored as text, and so that I'm able to easily convert it to be numeric by doing apply, and applying to the columns of interest here. That C12 means apply to every element in the matrix, and apply what? I'm applying the function as numeric. So then I'm doing a principal component analysis. I'm using PR comp, so this is different than what I did before. I used the eigenfunction before. So in R, there are many different ways to do the same thing, and there are many different functions for doing principal components. And in the optional lab, I'll post next week. I'll show you a few different ways to do this. So next, I am going to construct the biplot, that's what I'm doing here in these first few lines. So I'm using fit.x or fit $x, and then I'm adding the points afterwards. Okay, so those are our principal components in the fit $x. Now I'm adding some lines to it. I'm getting my matrix of eigenvectors. That's called rotation in this package. And then I'm going to getting some information in order to scale these red vectors to figure out how long they are. And that's what's going on in those next few lines. And then the bottom two lines I'm using to create those line segments emanating from the origin. Okay, so you'll play around with this code more in your optional lab, and obviously you can download the data and play around with this as well on your own. Okay, so let's talk about robustness in PCA for a second. So can an individual data point influence principal components analysis? Yes, absolutely. So an outlier can change an estimate of variance. We know that, right? If a point is very large or very small, it's going to increase the variance of a particular column of data. So in PCA, we choose vectors to explain as much of the variation as possible. And we know that our empirical covariance or correlation matrix is sensitive to outliers. So in fact, you looked at this in your homework earlier in the term. So one thing we could do is use a robust method to estimate the covariance, and many of these methods exist as a diagnostic to see whether or not there are outliers influencing principal components analysis. You can use a jackknife and look at the values of the first few eigenvalues as we drop points. So again, we're looping through the data, dropping one of our points, running principal component analysis on the data without that one point, and then say storing the first K, or L, I guess that's the right one, the first L eigenvalues. And then we can make plots for each of those eigenvalues as we've learned to do. So then we're able to see which points influence the fit the most. And there are also many other ways to do robust PCA, and many of these are implemented in R as well. Okay, so finally, so PCA will not always work. It may not always be a good solution. So one of the preconditions for PCA is that we have some redundancy in the columns of information. However, if the columns in our data matrix are uncorrelated, then PCA won't make much sense. And we'll have an example of this in your optional lab where you'll analyze full factorial experimental design. Okay, so this is the first of a series of short lectures on dimension reduction techniques. Thank you for watching, and yeah, take care of yourselves. Thanks.